Welcome, everyone. So, today we've got a truly fascinating explainer lined up for you. We're going to uncover the hidden reality of exactly what lies beneath our feet. I mean, get ready to completely shift your perspective because we're breaking down the incredible architecture of our planet and, frankly, solving some major underground mysteries while we're at it. Let's just dive right into this with a question that honestly puzzles a lot of us. If there is so much water right beneath our feet, why doesn't the soil just melt away? Like, why doesn't the ground simply sink or collapse under our own weight? It's a totally fair question. So many of us picture this massive, hollow cave underground, right? Filled to the brim like some endless hidden ocean or a giant subterranean lake. We kind of imagine that if you just dig deep enough, boom, you hit a massive, echoing cavern of water. But, well, that's a myth. The myth is that there's this giant water tank down there. Think about it. If that were actually true, the ground would be incredibly unstable. The earth could literally cave in at any moment, and water would just randomly burst through the surface. The reality, though, it's much more stable and, honestly, a lot more fascinating. The water isn't just sloshing around in some empty cavern. Instead, it's trapped, safely trapped within tiny, microscopic pores of soil, sand, and solid rock. Okay, think of the ground beneath us like a giant sponge. If we actually visualize this, like zooming in with a 3D animation, you can see how a sponge appears totally solid from the outside, right? But inside, it is packed with thousands of tiny little holes. And that is exactly where the water is stored. It doesn't pool into an underground lake, it fills up those tiny empty spaces between the rocks and grains of soil, forming this vast, hidden, intricate network. Now, this trapped water is what we actually call groundwater, and it's organized into these systems known as aquifers. You can think of aquifers basically as underground layers made of sand, gravel, and porous rock that act like massive natural storage tanks. And here is the absolutely crucial point. Water in an aquifer doesn't rush along like an underground river. No, it moves incredibly slowly. We're talking maybe just a few meters over several years. And that slow, super controlled release is exactly why water doesn't just spontaneously erupt the surface all around us. So to really wrap our heads around why this whole underground system stays so perfectly balanced, we actually need to take a quick journey downward. We're going to travel right through the Earth's internal structure, the crust, the mantle, the outer core, and finally, the inner core. Each of these layers has its own very specific job, pressure, and temperature. All right, step one is the crust. This is our life-sustaining top layer. Now, it's actually incredibly thin compared to the rest of the planet, but obviously it's the most important layer for us because this is where, well, life exists. Our cities, our forests, our rivers, they all sit right on top. And right beneath the surface of this crust is where all of our accessible groundwater and aquifers are hanging out. Basically, every single time we dig a well or pump water for drinking or farming, we are pulling it directly out of this very crust layer. But what happens when we go deeper, down into the mantle? Now, the mantle is massive. It extends about 2,900 kilometers down. The pressure and heat here are so intense that the rocks aren't even entirely solid. They actually flow, just very, very slowly. You'd probably think water couldn't possibly exist down here. But incredibly, and this blew my mind, scientists have discovered that the mantle holds a massive amount of water. We're talking potentially more than all our surface oceans combined. But there's a catch. It's not liquid water. It is entirely trapped inside the molecular structure of a specific mineral called ringwoodite, so it's locked away deep in the rock, completely inaccessible to us. Diving even deeper, we hit the outer core. Now, this layer is basically a bubbling, boiling ocean of molten iron and nickel. Think of it like a swirling pool of extremely hot liquid metal. The temperatures down here are so absolutely extreme that if even a single drop of water were to somehow make it down this far, it would instantly vaporize into steam. So yeah, there is absolutely zero chance of water surviving in the outer core. But it's this exact swirling liquid metal that crucially generates the Earth's magnetic field, which is what actually protects us all from the sun's dangerous radiation. Finally, we reach the dead center, the inner core. This is definitely the deepest, most mysterious part of our planet. Get this, the temperature here is estimated to be as hot as the surface of the sun, thousands of degrees Celsius. And yet, despite that unimaginable, literal sun-level heat, the inner core is a solid ball of iron and nickel. Why? Because the pressure from the weight of the entire planet pressing down on it is just so intense that the metals physically cannot melt. Naturally, in this extreme environment of crushing pressure and blistering heat, water and life are completely impossible. Okay, so let's jump back up to the surface for a second. If we are constantly pumping all this water out of the shallow crust, why doesn't it just run out? The answer is nature's ultimate recycling program, the water cycle. The sun heats up surface water, turning it into vapor. That vapor forms clouds, the clouds drop rain. Now, while some of that rain runs off into rivers, a huge portion of it slowly seeps down through the soil and rock. It refills those aquifers and becomes groundwater all over again. It's just this continuous, beautifully balanced loop that keeps our underground sponge perfectly hydrated. But as you might have noticed in your own neighborhood, digging for water isn't just a uniform, guaranteed experience. Sometimes you hit water just a few meters down. That's what we call shallow groundwater. In other places, though, you have to drill a massive, deep bore well through multiple layers of tough rock just to find a usable aquifer. The simple fact is, water just isn't distributed evenly beneath the earth. And the reason for that uneven distribution really comes down to two specific scientific properties: porosity and permeability. Let's imagine another 3D animation here to really see how this works. Porosity is all about storage, literally, how many tiny holes exist in that rock or soil. The more holes, the more water it can hold. Permeability, on the other hand, is about flow, how easily water can actually travel between those holes. So sandy soil has high permeability, meaning water fills it up really quickly. But clay? Clay has incredibly low permeability. It acts like a literal wall, completely blocking the water's path. And that's exactly why water levels vary so wildly depending on where you're standing. Now, there is a pretty shocking paradox to all this peaceful, slow-moving groundwater. Every now and then, water actually manages to seep deep enough to come into contact with boiling hot magma. When that happens, the water flashes into steam instantly, and this creates an immense, just incredible amount of pressure beneath the earth, like so much pressure that it can actually shatter solid rock and trigger explosive volcanic eruptions. It's wild to think about, but the exact same water that sustains life up here on the surface can actually be the catalyst for massive, violent destruction from below. But hey, volcanoes aren't the only threat to our ground stability. We are. Let's look at the very real-world domino effect of over-extraction. When we pump groundwater out way faster than the natural water cycle can replenish it with rain, those aquifers start to empty out. And because that water actually helps bear the weight of the earth above it, removing it weakens the supportive layers entirely. The result? The ground literally begins to cave in and sink, and local wells run completely dry. And this isn't just some abstract theory. It is a serious, urgent reality happening today. Look at places like Mexico City. Because of severe groundwater over-extraction, the ground beneath the city is literally sinking year after year. It's causing buildings to crack and whole streets to buckle. We're actually seeing similar alarming land changes in parts of California as well. I mean, if we don't give these aquifers the time they need to refill, the very foundation of our cities is at risk, and the struggle for basic drinking water is going to become really severe. All right, let's shift gears for a second and bust a very common everyday myth about groundwater. Have you ever paid attention to the temperature of well water or water coming from a hand pump? Depending on the season, it can feel surprisingly cold or, honestly, wonderfully warm. Now, because we know the inside of the earth gets hotter the deeper you go, a lot of people just assume the water should always come out hot. But actually, the baseline temperature of shallow groundwater is almost always a constant 20 to 25 degrees Celsius all year round. So the really crucial point here is that the water itself isn't magically heating up or cooling down. It's an illusion completely created by the outside air temperature. Think about it. During a scorching summer, when the air is burning up at 40 to 45 degrees, 25-degree water feels beautifully, refreshingly cold to our skin. But in the dead of winter, when the outside air drops down to 5 or 10 degrees, that exact same 25-degree water feels like a warm, cozy bath. It's literally just biology playing tricks on our senses. Well, we've covered a lot of ground today, literally. But I really want to leave you with one final mind-bending thought. Some of the groundwater trapped deep within these aquifers isn't just hundreds of years old, it's millions of years old. The water sitting in your glass today has been through this entire water cycle countless times. It has been a cloud, it's been a river, and yes, it might have actually been consumed by a dinosaur millions of years ago. So I'd love to hear from you. In your area, how deep do they have to dig to hit water? Think about the incredible ancient journey of that water the very next time you take a sip. Thanks so much for joining me for this explainer, and definitely keep your curiosity flowing.